I started this training. Just give me 1 minute. All right, let's start. So in week 1 and 2, we have studied some foundational things like vectors, matrices, Gaussian elimination, solving a system of linear equations in general. The first concept in week 3 is that of vector spaces, which is probably the first abstract definition. So I'm not going to write down all the axioms. I'll just copy it from the lecture slides. What is a vector space? A vector space is just it's a set V along with operations plus, which is from V cross V to V. What does an operation from V cross V to V mean? It takes input as two vectors and gives the sum of the vectors. Since we are using plus for it, we'll call its output as the sum. It's just a function from V cross V to V, meaning it will have something like VW as inputs, and strictly speaking, it is plus of VW is what you have to write, but for convenience, we'll write it as V plus W. And there is a second operation for which, once again, there are two inputs, but one of them is a real number and one of them is a vector. And the output is another vector, which is written as C dot V. And in many cases, we drop the dot and we just write CV, such that the following axioms are satisfied. These axioms, so a vector space, the general notion of a vector space is something that generalizes whatever we know for Rn. For vectors in Rn, we know all of these properties. I'm not going to go through each one of them, but addition is commutative, associative, identity, inverse, all of these things are very well known for vectors in Rn, or Rn as a set, and plus and dot is just addition of vectors and multiplication of a vector with a real number. This is known for when V is equal to Rn. But we are generalizing this and we are saying that any set for which we can prescribe plus and dot. Now the plus and dot need not be, the set itself could be Rn and we could have some alternative definition. I'm sure you have seen examples of that sort as well. As long as we can prescribe the sum of two vectors and the scalar multiplication or a real number multiplication of a vector in such a way that these 8 properties are satisfied, such a triple, this V plus dot, the set of 3 objects, one set and 2 operations, is called a vector space.
Sir, I have a small question here.
Yeah.
What is the difference between subspace and subset, and what is the condition of that null vector being in subspace and subset? That I cannot understand.
Okay. So I'll come to subspaces in a bit. For now, I'll just recollect some properties of vector spaces, and when I come to subspaces, I'll clarify that. Is that fine?
Yes, sir.
Okay. So the examples of vector spaces, we have things like Rn is the most standard example, the most trivial example of a vector space. And then if you have a system of equations, a homogeneous system of equations, then the set of all solutions to that system of equations, that is a vector space, something that you can verify. Then you can do polynomials, matrices. So M cross N, meaning matrices of order M cross N. This is also a vector space. All of these are examples of vector spaces. Now, the abstract definition is important, but for most of the examples that you will be dealing with in the course, you will be dealing with Rn or subspaces of Rn. So just to get used to the abstract definition, let us see this one non-trivial uh, vector space. So I'll redefine plus in a different way. In all of these cases, the operations are obvious. So you have vectors in Rn itself or matrices. You know what matrix addition is and scalar multiplication of a matrix is. But what if we do something different? So suppose I define plus from, let's say, uh, R2 to R2 itself. Sorry, R2 cross R2 to R2. So here I say xy plus x prime y prime. This is just the same, but I changed dot. Dot has to be defined, recollect, from R cross R2 to R2, scalar multiplication of a vector with a real number. So C dot xy, suppose I call it x comma 1. So, okay, Cx comma 1. So this is also a function, right? So I given a real number C and a vector x comma y, I'm telling you what it means to say C dot xy. I'm not doing the usual thing where I'm doing Cx comma Cy. I'll be doing Cx comma 1. Now, what are the axioms that this R2 along with these operations satisfies and does not satisfy? Can we quickly take a look at that? Can you tell me which one it does and which one it does not?
First and the second property holds. The third property also holds. The fourth property as well holds.
Yeah, so the
But we
first
need
four, the thing is it only depends on plus. So
Yeah,
the
so that's
plus
the
is
thing.
not changing. So 1 to 4 are okay. Now the thing starts with 5. So let's see 5. Does 5 hold?
I think no, sir.
No, sir.
5 does not hold, right? Why does 5 not hold? So 1 to 4 is okay, is satisfied.
Because 1 into x comma y will give me x comma 1.
So for 5, if I write 1 into, okay, let us take a particular example. Let's take 1 comma 0 for that matter. What will I get as the answer to this?
1
1
comma
As
1,
1.
which is
So
not
1
equal to
comma 1.
b.
Yeah. So, but what is required over here? For each element v, 1 dot v is equal to v has to be satisfied. So if you want to say that some property is not satisfied, you have to just exhibit one example. So if some property is stated for all v, then giving one single example where that property does not hold is enough to conclude that that property does not hold. What about 6, 7, and 8?
The 7 is equivalent to that of the same statement, c times v is not equal to cv here.
It's not equivalent, no? So you're saying 7 is equivalent to 5?
No, I'm saying that it's equivalent to saying that c times v1 plus v2 is not equal to cv1 plus cv2 here, because of the identity that c of x comma y is not equal to c of x times cx comma cy. That would be equal to cx comma 1.
It is Cx comma 1, but what is the guarantee that, like, why are you saying that 7 does not hold? You have to give an explicit example, right? There could be non-standard examples where 7 holds. So let's take up 7. If I do, what is the thing that I have to verify? C times V1 plus V2, is it equal to CV1 plus CV2? So let me take something like this itself, right? So if let's do just this. So this is the left-hand side of the equation. Here, what would this be? It would be 1 times 1 comma 1, which by definition is just 1 comma 1. On the other hand, the right-hand side is 1 times 1 comma 0 plus 1 times 0 comma 1. This thing. So what is that? That is 1 comma 1 plus 0 comma 1, which is what?
This should come out to be 1 plus 1 comma 2.
Yeah, so this is not equal to this.
We could have taken just two generic vectors x, y, and x prime, y prime, and we could have done this in a generic way, right? C of x.
Yes,
plus
we
x.
could have done it in a generic way, but there are some vectors for which that holds also. Right. So if I do it generically, if I do C x y plus x prime y prime, so this would be equal to C times x plus x prime, comma 1, after all the things are done, because your y plus y prime will not matter.
Yes.
So on the other hand, your cxy plus cx prime y prime, this would be
Cx plus 1 and
okay.
Cx prime
You'll
plus 1.
always have 2. Yeah, in this
Yeah,
case,
that's right.
that's true. Yeah.
Yeah.
In this case, you will always have 2. So you'll have 1 and you'll have 2.
Exactly,
So
because
this,
of that's what I was saying.
yeah. In this case, you can take a generic thing. Yeah. In fact, the polar opposite of 7 is true. Like for each element, this will not be true. That is the statement that holds in this case. Anyway, what about 6 and 8?
I think that's also true. Like that also doesn't hold true for the same reason as well. Because if you take 6, for instance, 6 can be written as 2 into 3. So 2 times
So
3
if
times
you
2.
have something like C1 times C2 times XY, this would be C1 times C2X, comma 1, which is okay to be C1 C2X, comma 1. And on the other hand, C1 C2 XY is also C1 C2 X1. 6 holds, no?
Yes. 6 volts. Yes.
6 holds.
Yes.
And 8, what about 8? 8 once again will not hold because a plus b times some xy will have second coordinate as 1. But a times v plus b times v will have second coordinate as 2. Check that this does not hold.
Sir, in the exams, will be given the axioms or we will remember this?
You have to remember, and you'll not be asked things like choose the operations for which
In PYQ,
axiom
this
4
type of
does not.
question is not there. This type of question is not in PYQ.
But that does not mean anything, right? It could come in this time around. Yeah. So there's one more thing that this is called the additive identity.
And b prime would be the additive inverse.
Yeah, this is called the additive inverse. So just to get a little bit more comfortable with the abstract definition, consider this definition of. So my vector space over here is positively inverse, strictly positive. That is It's just R plus, which is X in R such that X greater than Z. Let me do this. So I'll define X plus Y as XY. Now, instead of addition, the usual addition is defined as multiplication, and C times X is defined to be X to the power C. So does this have an additive identity? If so, what is the additive identity? Let's just worry about additive identity. Does V plus dot
So the additive identity would be the usual additive identity 0, 0, right?
there's no 0, 0. My set is positive real numbers.
Okay, you have said the x greater than 0. Okay.
So what is the answer? Does it have an additive identity?
No, sir.
So what is the additive identity? As in, what is the element that you would call the additive identity?
Such
Additive identity.
element such that x plus that element should give x upon doing a vector addition.
Additive identity is let's me call it x naught. X naught belong to R plus such that x plus x naught is the same as x naught plus x is the same as x. I think this is what you were also saying, right?
Yeah.
Yeah. But what is x plus x naught?
The x into x naught.
So this is x naught. This is x naught x. So does there exist an x naught which satisfies this condition?
And that would be 1, 1 only. I mean, the vector
so-
would be 1, 1.
Not 1, 1. There's no two coordinates. There's just one. So x naught is equal to 1.
Why not as well, no?
There's no y naught. We are just dealing with R plus. It's not R plus cross R plus or anything. It's not a two-dimensional
There's
space.
only one-dimensional space. Okay.
Yeah. So x naught. So 1 is the additive identity over here. This is not the usual operations. So this 0, you should remember, is just a symbol. That 0 need not be 0 always, the 0 that you know, the 0 number, even in cases like R plus, in subsets of R. So did you understand why this is the additive identity?
Yes, sir. Yeah.
Yeah. And as an exercise, you can go and check that this is actually a vector space. This would be a good exercise to do for your understanding and dealing with abstract definition of plus and dot as opposed to the usual addition and subtraction. And what is the next thing? Okay, before we go to linear dependence, we need some properties. I'll just state them. All of them are fairly obvious. These are not all of them. These are just a list that I've just made.
Sir, your handwriting is very good, actually.
Thank you. So this is called cancellation law. This, once again, you know very well for real numbers as well as vectors in Rn. This holds for abstract vector spaces as well. Then you have additive identity. Is unique. additive inverse is also unique. The proofs of all of these I'll not give. I'm just stating this to recollect it. Minus c, the real number minus c when scalar multiplied with the vector v is the same as the additive inverse of the vector cv, which is the same as c times the additive inverse of this.
Sir, unique here as in what we is it?
So unique meaning if x plus y, sorry, if x naught and let's say x naught prime satisfy, what was that axiom? Probably 3. Let me just verify that later. Then x naught is equal to x naught prime. So what does the condition 3 say? There exists an element. Oh, sorry. What have I done over here?
See, that should be additive identity. And you ruled out with additive inverse.
No, additive identity is fine, right? Yeah, this is 3 is additive identity. Correct. So if there are two elements such that v plus that element is equal to v, and so two elements x naught and x naught prime such that v plus x naught is equal to v, and v plus x naught prime is also equal to v, then x naught has to be equal to x naught prime. This again follows easily from cancellation law. This is a corollary of the cancellation law. But it says that even though 3 guarantees that there exists, it's actually there exists a unique element. There cannot be 2 elements satisfying the same property. So when you refer to 0, it is a specific element. All right.
So in number 4, is it the 0 vector or the 0 in real numbers?
0 scalar. So you cannot multiply a vector with vector. That is not discussed here. So the operations that you have are scalar multiplication of a real number with a vector or addition of 2 vectors. So in this case, from context, it will be clear what is happening. So if you have multiplication of 2 things, it will be a real number with a vector. So 0 the real number with the vector v. So this, all of these hold for all v, v1, v2, v3. So all of these properties. So those are some of the properties of the vector spaces. And now we come to subspaces.
Sir,
Sir, can you explain the previous? You said the previous vector vector which is given in single dimension R is a vector space. How
Yes.
additive inverse is true for it? This one, yeah.
Yeah, okay.
Because
Additive
0 doesn't
inverse,
exist, no?
0 is not there. 0 is not there in my set also. So what do we need for additive inverse? Given an element x, I need to produce some element such that x plus that element is equal to the additive identity. And what is the additive identity over here? That is equal to 1.
Okay, you should not assume it to be 0. It should be additive.
Exactly, exactly. That's why I said this is a good exercise. So this 0 is the 0 vector or the additive identity. So let me just call this 0v.
Okay, but even if we take that condition also, but vectors are limited to positive side, so
Yes.
x plus something can never be 1. It can't.
But what is x plus something? By definition, it is x times something, right?
Yeah.
So this something will be, let me not keep calling it something. Let me call it x prime. X prime. So x prime is 1 by x. Now 1 by x does make sense because we are excluding the 0.
Okay. Yeah. Yeah.
Right. So this is the additive inverse.
Sir, can you do one scalar multiplication thing for that when so many are there?
For this example, is it?
Yes, yes. Cx is equal to x to the power of c. Because
Let us do it at the end,
okay, sir.
maybe,
No.
because
Yeah.
we have quite a few topics to cover still.
Okay.
So,
Yeah.
so will you please explain with example all of these properties on real number?
The properties for real numbers, it is easy to see. So when you have v1 plus v2 is equal to v3
Like
plus
how
v2.
can I relate with these properties?
For now, I think I'll skip it because whenever you have problems, only you will be using this readily. So there's not really examples that I can show you, but proofs of it, but that is not required, I think. Proofs of it will not be useful for you. But all of this, when you're doing other problems, you will be using it. So for now, I'll skip it.
Like
Maybe
I know the properties, but how can I relate with these?
so when we talk about a linear independence and all that, I'll tell you how you're implicitly using these
Okay.
without actually maybe acknowledging the use of it as the property. Here, we most of the time just assume those things are true because these are all obvious looking properties. Okay. So a subset W of V plus dot set to be subspace if the following conditions like V plus W is in W, or let me call it W1 plus W2 for all W and W. Now, what does this mean? It means that if you take two elements from the subset and if you add them, that element also has to be in the given subset. It should not, the addition operation should not take elements outside the subset. Similarly, scaling vectors also should keep you within the subset. So in such a case, we call this thing a subspace. A subset could be anything, any collection of elements which
Sir,
is a subcollection of V is a subset. Yeah, go ahead.
zero vector should also be in the subspace.
That will follow from this because if I take for all C and for all W, I could just take C to be 0 and any W, and then that would mean that 0 is in. This is because of the axioms or properties. We have that 0 dot W is always 0.
Okay, sir.
So this follows from that. So that need not be stated separately. If you can check these two things, you're done. So there was earlier a doubt about clarification regarding subset, subspace, and all that. Was it you who asked it earlier? I guess not. Uh, yeah, whatever clarification you need, right? You should speak up now. Okay, all right. Now let's take some sort of a simple example where we have R2. And let's take the parabola, assume that it's passing through the origin. It's like y is equal to x squared. So the points of this, meaning w is equal to x comma x square, x belongs to R. Now this is a subset of R2. R2 is a vector space with the usual operations. R2 is a vector space. Now, is W a subspace?
No, sir.
Yeah, why is that?
So
It
1
does not
comma
have any
1
negative.
stays there, 2 comma 4 is there, but 2 plus 1, 3 is not 5.
2 comma 4 is there.
1 comma 1 is there. So 1 plus 2 is 3. So 3 comma 5 is not there.
Yeah. Therefore, W is not a subset, a subspace. Addition of vectors should keep you within the set. That is not happening. Or you could just say 1 comma 1 is there, 2 comma 2 is not there, because you need also scales of it to be there. Right?
Sir, I have a small question here. Instead of a
Yeah.
parabola, if it was a line of the form y is equal to mx plus c, in which c had a
Yes.
value, then also would it have been a subspace or not?
No, it would
Because
not be, right? So
why?
if you have x plus y is equal to 1, for example, this is okay. So let me write this as an example. W is not a subspace. Things are a bit mixed up, but okay. Now y is equal to mx plus c. Let me take particular numbers, x plus 1. Now 0 comma 1 belongs to it. Belongs to, okay, so this set I'll call W. You have to write it better actually, x comma y such that y is equal to x plus 1. 0 comma 1 does belong to that set. And then let's take some other point, minus 1, 0. Both of these belong to the set. But what about their sum? Does it?
No,
No.
because if you take a generic vector, it should be x1 plus x2 and x1 plus x2 minus 2, so which doesn't lie in for,
Yeah.
which doesn't
Yeah.
belong to subspace level.
Right. So in general, or at least I just need one pair of vectors or one vector and a scalar such that the scaled vector does not belong in the subspace. You can come up with many examples, or you can work with the generic expression and see that not always does it hold. In this case, probably it never holds.
Sir, if I write y is equal to mx, for any value of mx, is it a subspace or not?
Yes, that is true. So if you have x comma mx, where m is m is a fixed constant. So x is in R, m is arbitrary but fixed. So let me call this Wm. What is Wm? It's this line of slope m. So in this case, you can verify that if I have x1 mx1 plus x2 mx2, the sum is x1 plus x2 m times x1 plus x2. This is again in Wm, right? Why? Because elements of Wm are of the form first coordinate, comma, second time m times first coordinate. Second coordinate is m times first coordinate. And this is of that form. So this is on the line or in our subset of interest. Similarly, if I take any real number c and multiply it with an arbitrary vector over here, it looks like cx m times cx. Once again, this is an element of Wm. Does not matter what m I take. This argument always holds. Is that right?
Yes.
So this is a subspace. Wm is a subspace. In fact, you can take this as a fact without proof. The subspaces of what? First of all, this statement was not complete. The the subspaces of R2 are, can you give me the list?
One zero zero one
Zero R and
line through origin.
So this is a complete set of subspaces of R2. Y is equal to mx covers all lines through origin except one, and then the trivial subspace and R2 itself. So if you take the whole set itself, of course, it satisfies these two conditions. So you will get it as a subspace. The trivial subspace is also vacuously satisfies the given conditions, two conditions. So that will also be a subspace. And the non-trivial ones. So this one and this one, it's not just for R2. You will always have the single element additive identity subspace and the whole space as subspaces. These are called trivial subspaces, and then you have non-trivial subspaces. The only non-trivial subspaces of R2 are lines through origin. Similarly, for R3, you can see that it is going to be the trivial subspaces, which is 0, 0, 0, and R3. So note that this 0 is actually the single element set, which is 0, 0. 0, 0 is the additive identity. I just wrote it as 0 because in the vector space, it acts like the 0. So for R3, it will be the origin, the single element set containing the origin, R3, and then you have lines through the origin and planes through the origin. So there you have a few more. Okay, so that's subspaces. And maybe one more comment is the solutions to A. This is an M cross N matrix. AX is equal to 0 is a subspace of R. What is the exponent? It's a subspace of
Rn.
which Rn, right? The solutions would be over here. So what is X? X is actually an N cross 1 matrix or a vector of order N. So the solutions are a subset of Rn and they happen to be a subspace as well. So this subspace will be later on, we'll revisit this subspace. So because of the addition and multiplication structure, what we can do is express certain elements as linear combinations of other elements. So that's what we'll see next.
Sir, would you please explain me the subset and subspace difference?
Subset is any subset. Subset, you know, right? Now, a subset which satisfies these two conditions is a subspace. For example, this W is a subset, but it is not a subspace. Why? Because it does not satisfy the closure under addition. So this is also called closure under addition, closure under scalar multiplication. It doesn't even satisfy closure under scalar multiplication. A subset could be any subcollection of the given vector space. So if you take R2, any subcollection of R2, even if you just take 2, 3 points, that's also a subset. But if you have some elements in that subset, and if you add them, you should have that sum also in the subset and scales of those elements also in the subset. Only in that case, you can call it a subspace. So this is not a subspace, this is not a subspace, but this is a subspace. Why? Because these two conditions are satisfied. Subset plus these two conditions is subspace. Is that fine? Just see. So if I'm given finitely many vectors, then I can scale these vectors and add these vectors. So any such combination, scaling the given set of finite vectors with possibly different scalar multiples and then adding them gives me a linear combination. So this is a vector, right? If you scalar multiply a vector with a real number, you get a vector, and then you add those vectors, you get another vector. So this is a vector. So this is a vector which we say is a linear combination of v1, v2, vn, or a linear combination of v1, v2 is any vector, v1, v2, vn is any vector of the form c1, v1 plus c2, v2 plus cn, vn. So one question is zero vector a linear combination of given some finite set v1, v2 up to vn? Is zero a linear combination of this?
Yes, sir.
To check that, what do we have to do? We have to write zero as c1, v1 plus cn, vn, and see if this equation has a solution. But this equation always has a solution. What is it?
That is the C1, the Ci is at 0, the trivial solution.
Yeah.
Trivial solution.
Ci is equal to 0 for all I is always a solution. This is to be compared with the homogeneous system of equations always has a solution. Even though these vectors may not be in Rn, this is something very similar to that. But then when does it have non-trivial solutions? This leads us to what is called linear dependence. A set v1 to vn, finite set, is said to be linearly dependent if has a non-trivial solution. So equivalently, why is this an equivalent formulation is not something that I'm going to prove now. One of the vi can be expressed as a linear combination of the others. That's why it's called linear dependent, because one of them is actually a combination of the others. So it's not really independent. So I can, if I even remove it, then you'll not lose much, because that can be recovered by linear combinations of existing elements itself. So this is the way to work with it, but this is the way to understand. Like if you can write one as a combination of the others, it's in some sense redundant. So that is why it's called dependent. So, but for practical purposes, you will be dealing with this equation to establish linear dependence or independence. So what is independence? Not linear dependence is linear independence. If v1, v2, vn is not linearly dependent,
So how will I check that they are linearly dependent or independent by using matrix or determinants on this?
we will do that.
Mistake, it's not equal to 0.
Equivalently, we'll just write summation Ci Vi is equal to 0 implies Ci is equal to 0 for all I. If this happens, this is the same as saying that it is linearly independent. So, which means that the zero solution is the only solution. Zero solution is always a solution, but that is the unique solution. If you have something like that, then that is an equivalent formulation of linear independence. Now, that is all about the definition and all that. Now, how do we actually check? Checking linear dependence or independence. So first we'll take up some special cases. I'll just tell you what you can use to work out things. So the first special case is just set of two vectors. In this case, how do you check dependence and independence or independence?
Yeah, so you'll write this in the form of matrix, right?
And then we will
We can check
reduce it
for the
And
scalar
we check the
multiplication.
determinant if it's
These
equal
need
to
not be in
0.
R2. So this is just two vectors. It could be in any vector space.
We can check for scalar multiplication here.
Yeah, so S is linearly dependent if one of the vectors is a scalar multiple of the other. So this only works for two vectors. That's why I've written it as a special case. Is that fine? Because if we do something like C1 V1 plus C2 V2 is equal to 0, and if it has a non-trivial solution meaning C1 or C2 would be non-zero. Suppose C1 is non-zero, the other case is similar. Then I can write V1 plus C2 by C1 V2 is equal to 0. And then I take it to the other side, I get V1 is equal to minus C2 by C1 V2, which means it is a scalar multiple of the other. So for two vectors, all you need to check is one the multiple of the other? So you have to check for both things. Is V1 a multiple of V2 or is V2 a multiple of V1? If either of them holds, then they are linearly dependent. Otherwise, they are linearly independent. That's a very special case, only two vectors. Set S containing the zero vector.
So please explain once previous.
Okay, so suppose you have, I'll give an example maybe. Let's take something like 1 0 1 1 1 0 minus 1 minus 1. These are vectors in R4. So there were some suggestions of let's write it in a matrix and take the determinant and all that. This you cannot do over here, you see, because you will get something like a 2 cross 4 or a 4 cross 2 matrix. So in this case, how do you check? Are these linearly dependent or independent? Can I write this as a scalar multiple of this or this as a scalar multiple of this?
No, we can't write it.
No.
Yeah. So that is why this is linearly dependent. If you cannot write one as a scalar, sorry, this is linearly independent.
Independent, right? Yes.
Yeah, this is linearly independent. Dependent meaning it's a scalar multiple of the other. So the only way a two element set could have dependence is by scalar multiplication only.
So like one set is 1 comma 2 and the second is 2 comma 4.
That is dependent.
Yes.
Yeah, because one is a scalar multiple of the other, right? So
like
yeah,
this
but this
method is
yeah,
for non-square sets.
it is just for two vector sets. It's only for a set containing two elements, set of two
Okay.
vectors.
Yes.
Right? So yeah, that is the first special case. The second special case is set S containing a zero vector. Whatever your set is, v1, v2, vn, and if it contains the zero vector, this is always linearly dependent.
Why?
Because just one. Yeah, because here linearly dependent meaning I can write 1 times 0 plus 0 times v1. So this is the zero vector plus 0 times v1 plus 0 times v2 plus 0 times vn is equal to 0. Right, so this is a non-trivial linear combination of the vectors because this, not all of them are 0, right? There is one non-zero vector. So if I write something like C1, let me pair these guys with their numbers itself. If I do this, plus Cn plus 1, 0 is equal to 0. This equation has a non-trivial solution. Non-trivial solution being 0, 0, 0, 0, 0, 1.
So non-trivial solution, you can say heterogeneous.
This is not a heterogeneous system of equations. So it's not, we are not talking about homogeneous or non-homogeneous system of equations, but I'm just writing, can there be a non-trivial linear combination which equates to 0? In this case, the answer is yes. And if that is the case, then it is called linearly dependent. So going back over here, what did we say linear dependent was? If this equation has a non-trivial solution. In this case, it does, right? 0, 0, 0, 0, 1 is a non-trivial solution to the above equation. This is the zero vector. So any set containing the zero vector will always be linearly dependent. Is that fine?
Yes.
Next, we have n vectors.
So could you explain once what do you mean by the trivial solution and non-trivial solution?
So when I'm writing a linear combination and equating it to 0, so this is the check for linear dependence or independence. So if I have n vectors and I want to check if they are linearly dependent or independent, the fundamental definition is that you have to set up this linear combination equal to 0 and see if it has non-trivial solutions. What is non-trivial solution? So what are we solving for? We are solving for possible values of C1, C2, Cn, which satisfy this equation. The variables are C1, C2, Cn. But this equation always has a solution which is 0, 0, 0. All Ci's are 0. That will definitely satisfy this equation. But that is called the trivial solution. Any other solution is called a non-trivial solution. In other words, there should be at least one non-zero coefficient. All right?
Yes, sir.
Okay. So next, to check linear dependence or independence of n vectors in Rn. So note that this and this have to be the same. How do we do this? For this, I think there were some suggestions earlier. So use determinants. When you have n vectors in Rn, if I construct a matrix whose columns are these vectors, then I get a square matrix, correct?
Yes, because you have n and rn, so both the dimensions are equal. So
yeah. So if I take an example, 1, 1, minus 1, 1, 2, 3, 0, 4, something. Now this is a set of 3 elements in R3. So this satisfies this special case criteria. So I'll just write 1, 1, minus 1, 2, 1, 2, 3, 0, 4. What I need to do is construct a square matrix with columns being the given vectors. The rows also doesn't matter in this case because transpose has the same determinant. We need to compute its determinant, which would be something like minus 1 times 8 minus 6 plus 1 times 7. Hopefully this is not wrong. And yeah, the important point is, yeah, if it is wrong, just correct me. If determinant,
Which row did you expand, sir?
I used this because there was a 0 there. So 8 minus 6 is 2 and 1 times 4 plus 3 is 7. Yeah, I think it's correct. So this is in general. If determinant is 0, then linearly dependent. If determinant is non-zero, then linearly independent. Compare with Ax equal to 0 when A is a square matrix. So when A is a square matrix, Ax equal to 0 always has a solution. 0 is always a solution to the homogeneous system of equations. But when is it a unique solution? And when are there infinitely many solutions?
So infinitely many solutions if there is one free variable, one or more free variables left out in your
It is
equation.
zero, there will be infinitely many solutions, and when it is not equal to zero, there will be unique solution.
Right.
So
So
for
if the determinant is non-zero, then you can multiply by A inverse both sides and X is supposed to be equal to 0. So you will have the only unique solution. And if determinant is 0, you will have infinitely many solutions, which is the same as there will be at least one independent variable. One independent variable meaning that can take any value, right? So that means there are infinitely many solutions. So it's the same over here. Determinant is not equal to 0 means my linear combination will have the unique trivial solution. So that may be one way to remember. If it is confusing, then forget this comment. You can just remember this part. That if determinant is 0, then it is dependent. If determinant is non-zero, then it is independent. Now, all of these are special cases, but the most general case is something similar to Gaussian elimination. If S is, let's say, V1, V2, Vn in some vector space V. Now, I am not assuming it is in Rn. I'm not assuming the number of vectors is the same as the dimension, or I'm not assuming it has a 0. There might be more than 2. All of this. This is the most general case. So in this case, what you do is construct the matrix with Vi as columns. So yeah, row operations or get. Okay, I'll just say reduce the matrix. Reduce is just using Gauss elimination. What you need to do is solve. Let me call this matrix A. Solve Ax equal to 0. If there is a unique solution to this, then it is linearly independent. If it has infinitely many solutions, it is linearly dependent. Unique solution Once again, I'll give an example for this, otherwise it might be confusing. Unique solution implies linearly independent, infinite solutions. For Ax equal to 0, remember there's only two cases, unique solution or infinite solution. And these correspond to independence and linear dependence. So let's take an example. 1, 1, 2, 3. 1, 3, 4, 5. And 1. Let me do something that I know is dependent. 1, 7, 8, 9. Now this is 3 elements in R4.
So this method can be used when it's not a square matrix, is it?
Yes, even when it is not a square matrix, but okay, this is in some Rn. Okay, so this is for not general vector spaces where you cannot write matrices. It is in some Rm, and you will be dealing with only subspaces of this form. In some Rm or subspaces of Rm, but let me not make it more confusing. So this is a
linear dependent, right?
Why do you say that?
Because V3 equals V2 minus V1.
Yeah, here you can see, but let me go through the procedure of how to do it. What does the first step say? Construct the matrix with VIS columns. So you do that. 1, 1, 2, 3. This is the first vector as the first column. Second vector. Third vector. Now, if I want to solve this system of equations, what is the system of equations? This times x tilde is equal to 0. I need an augmented matrix with 0, 0, 0, but I can skip the augmented matrix because it's on the other side, it's just 0. So how to solve this, I'll reduce this to REL. And to do that, what will I do?
R2 minus R1 and
Which
R3,
is this.
R3 minus 2R2.
2R2. So that will be again this.
R3
and
minus
R4.
3R3. R4, sorry.
R4 minus 3R1.
Yeah. So here we can do R3 minus R2 and and R4 minus R2.
First R4 minus R3.
Are you convinced that eventually you will get to this point?
Yes, R4 minus R3 and then R3 minus R2.
Yeah, and then R2 you divide by 3.
Yes.
So if I want to solve a system of equations for which this is the coefficient matrix, the homogeneous system of equations, will this have a unique solution or infinitely many solutions?
So infinitely many solution.
So infinitely many solutions. Therefore, S, I'll call this set S. This is linearly dependent. If I have a unique solution, then it is linearly independent.
Sir, it is infinitely because it has pivot of 2 points.
There is one independent variable, right? The independent variable could take any value. So what are the solutions to this? It is x plus y plus z is equal to 0 and y plus 2z is 0. So this z could be anything, but then y will be equal to minus 2z and x will be equal to z. So the solutions of the system of equations is of the form z 2z or minus 2z z. And there are infinitely many of them.
Okay.
So if there are no independent variables, then you will have a unique solution. And suppose the vectors that I started out with was say 7, 9, 9. Maybe I should not change this now. So assume that this 8 was a 9. In that case, what would come over here? You would get, instead of 3, 6, you would get 2 times when you remove, you will get 7 instead of this 6. And over here, when you do stuff, you will get a 1.
So we'll have a pivot in third row.
There will be a pivot over here also. In that case, there will be a unique solution, which would mean that that set is linearly independent. In other words, take it as an exercise if you want. 1, 1, 2, 3. 1, 4, 5, 6. 1, 7, 9, 9 is linearly independent. Now in problems,
Sir,
you might be, yeah, go ahead.
If it is fourth row is there in the set, so by adding a fourth row, which is having another vector fourth row in R3, so which will make the entire set as linearly dependent, isn't it? Because like you're saying it is linearly independent, yes, having a pivot element, but however, which has a unique element, but when we are adding one more vector in my R3, so which makes the entire set as linearly dependent, right?
It could or it could not. So it depends on what fourth vector you add, right? So this is in R4. These are vectors in R4, and you have a 3-element set which is linearly independent. The vector that you add might be a linear combination of the previous 3 or may not be. So it depends on what element you add. This is an R4, no? 1, 2, 3, 4.
Okay.
So if it was R3, then...
So can I write all these vectors in row form?
If you write it in row form, no. That will... So there, if you write it in row form, there you'll always get infinitely many elements, right?
Okay. So like
because
in
then it,
row form and in column form, answer will be different in these cases.
yes, this method is prescribed to write it as columns itself. Rows will not work.
Okay.
Sir, the pivots elements are in a row, column 1 and column 2. So can we say the first vector and second vector are basis vectors?
Yes, that will come to later when we discuss how to get a basis for a given subspace.
Okay.
But in this case, actually, it's not first and second row because we have written it in column form. No, so this vector and this vector will be a basis.
Yeah, that's what I was saying.
Yeah, the first vector and the second vector will be a basis. That is by the column method of finding basis.
Sir,
but in general, yeah.
Yeah, I have a doubt. Like, say for example, like we have given that B1, B2, B3 is linearly independent, and we are given some linear combinations of it, and we are asked to check if it is linearly dependent or independent. How do we do that? Like, V1 plus V2, V2 plus V3, something like that.
I didn't get. So you are saying abstract V1, V2, V3 is given?
Yeah, and some linear combination of it has to be checked as linearly dependent or independent.
Okay, so remind me at the end. We'll take it up because there are some topics to cover still. I'll take it up at the end.
Okay.
Okay, so this is about linear independence and dependence. Next, we'll go towards the basis of a vector space. So linear independence is a desirable property because you can express many vectors in terms of a finite set of vectors. But then at some point, you cannot make it linearly independent anymore. So there is a maximal linearly independent set. That is what we'll call a basis. But before we get to that, let's talk about span. Span of a set is set of all linear combinations using vectors from S. So just like we were doing over here.
So it includes linearly independent and linearly dependent sets, right?
Which one?
Span will be included linearly independent and linearly dependent vectors as well, right?
So vectors are generally not linearly dependent or independent, right? So it's a set which is linearly dependent or independent.
Yeah. So
yeah, by definition, you are including all possible linear combinations. So you will have, so take for example, the span of S is always linearly dependent because it contains linear combinations of existing elements. If that is what your doubt was.
span includes both linear independent and linear dependent sets, right? Or only linearly dependent?
Span is a set of vectors. So it is all possible things like this, where Ci is in R and Vi is in S. Finite linear combinations of this sort.
Okay.
Okay, so by definition, span of S is a linearly dependent set. But yeah, that is kind of a trivial observation.
Sir, one more doubt here. Like, say for example, let's take one vector that is considered to be a span from the set. Is it always mandatory that that should be a part of S?
Give me a specific example, maybe.
Okay, say for example.
Sir, I'll tell you.
Like
two vectors that span xy plane in R3. So 1 0 0 0 1 0.
Okay. So this is your S.
Yes.
What is
now,
span of S?
Yeah.
Span of S is all possible linear combinations of vectors from this. So you can take x times, or let me just call it C1 as we have been doing so far. C1 times 1 0 0 plus C2 times 0 1 0. C1 and C2 could be any real number values. So this would be C1, C2, 0. And C1, C2 are arbitrary. So you have the entire xy plane. You cannot do anything to the z coordinate. So what is span of S? This is actually xy plane.
Yeah, so sir, can I add a vector that adds a z?
Size span means all possible values in any vector.
You can take the vectors from your given set and multiply them by any scalar, any real number.
Yes.
And add them, take linear combinations. You do all possible, and the set of all vectors that you obtain this way is called the span.
Okay, but the values will be in vector which I find after add and multiply.
Yeah, that is, it's supposed to be a subspace, right? It's supposed to be a subspace of your vector space. So it will consist of vectors only.
Okay.
The set of all vectors is what I'm saying, right? Set of all linear combinations, meaning they are vectors.
Sir, what's confusing is, let's say this S is a space. We discussed it's an xy plane in R3. So
S is not the xy plane. S is just a two-element set 1 0 0 0 1 0. The span of S is the xy.
Okay.
Yeah.
So if I add another vector, which is 0 0 1, which adds the z coordinate, will it?
You're adding that to S or the span
yes,
S?
Yes, I am. Oh, that matters.
So if you do S union 0 0 1, so what is your doubt?
Yeah, so can I still say it spans xy plane? Because it can, but it spans more than xy.
Yeah, that should not, like that's not correct. As in a spanning set for a subspace should contain vectors of that space itself. But yeah, there are some conventions where as long as there are at least those many elements, they say that it's a spanning set.
Yeah, that is. I saw one of the questions which contradicts. That's okay.
Where there was this thing, right? So I think it was last year itself that there was
right. Yeah.
Yeah,
Yeah.
like
So
it was a matrix related question. So basically, they have asked for the symmetric matrix, and they gave like a trivial thing 1001 such basis. So even that
yeah,
will be
there
span, right?
were more than that, right?
Yeah, yeah, correct.
It would span more than that.
Yeah,
Yeah, I have seen that question. Yeah, we have made it a point to avoid such confusions like that. That was, yeah.
Yeah. So,
That was
but
not a well formulated question.
what's the
Yeah.
convention? Like, what
The
what do you
convention
guys think?
is that if you want to say that something is a spanning set, it should contain vectors from that set itself.
Like, so every single set in that spanning set should be restricted to that.
The span should not be more than that.
Okay. Okay. Yeah.
The span should be exactly that.
Yes. Okay.
So if I were adding the element 001, so it won't be a span. Will it become non-span or what?
Yeah. So S union 001, is it a spanning set for XY plane? This was the question.
Yeah.
And we'll follow the convention that it is not.
Okay, but actually, as generally thinking, it's already spanning the XY plane. Another adding an independent vector, so it spans the entire R3.
Yeah, but then when you're defining basis as a spanning set which is linearly independent, if you allow for these things, so this would also be a basis for XY plane, which it is not. So this is why I want to avoid that.
Okay.
Do you get my point? Anyway, right now I think we should not spend more time on that because we should just accept this as the convention and move on because of lack of time and all that. So spanning set meaning you just consider that the span should be exactly equal to that. It should not be more than that. I get your point also that it does span XY plane, even if it is more than that. You're saying that just from an understanding point of view, it does span. But let us not
Yes.
Consider that. Let's have that the span should be exactly equal to what we are looking for. All right. So yeah, that's the span of a set. And a set S is said to be a spanning set for V if span of S is equal to V. Now, if I have a subset of vectors in a vector space such that every vector in the vector space can be obtained as a linear combination of these things and not more is what we are adding now, then such a set will be called a spanning set. So we want as few vectors in the spanning set as possible because we want to express every vector using as few vectors as possible. And that brings us to basis. Linearly independent spanning set for a vector space. Now we know how to check whether something is linearly independent using the row reduction and seeing if that has a unique solution. Similarly, spanning set also, if you take a generic vector in the given vector space and try to write it as a linear combination of this given set, this will lead to a system of linear equations, see if that has a solution. So that is how you check if something is a spanning set. That is how you check if something is a basis. So two conditions need to be checked. Whether the given set is linearly independent and whether it is a spanning set. Now, equivalent formulations are maximal linearly independent set or minimal spanning set. So what does that mean? If a set is linearly independent and adding any vector makes it linearly dependent, then we call this a maximal linearly independent set. For example, take 1, 1, 1 minus 1. Is this linearly dependent or independent?
Independent.
Independent.
Independent, because one is not a multiple of the other, or you can do the determinant or whatever. Now, if I add a third vector, v3, does not matter what it is. Let me add something like a comma b. A third vector I'll add to this set. If I check linear independence of this, you'll see 1, 1, 1 minus 1, ab. And if I row reduce it by just doing the row operation, what happens? This remains as it is. And this becomes b minus a. And I'll divide by minus 2. So I'll get something like this. And are there independent variables for this system of equations?
It becomes dependent.
Are there independent variables?
Yes.
Yes.
No.
Sir. Yes, sir.
Yes.
There
Last.
is, yeah, z is an independent variable. So there are totally 3 variables, 2 of which are dependent, 1 of which is independent. So there are infinitely many solutions. So this is a set of linearly dependent vectors. In general,
It is
if you have,
two, right, sir? So when we add a third vector, it will become linearly dependent.
yeah, now without this the talk about dimension and all that, we cannot do that. I'm just saying, even using first principle definitions, you can conclude this. In general, if I have m vectors in Rn and m is greater than n, what happens to the matrix? The matrix will have, so this, there will be m columns and n rows. It will be an n cross m matrix. Do you see that? Because each column is a vector. So the column, the number of rows is n and number of columns is m. So it has more columns than rows. So this is long, this is shorter. So even if you have pivots everywhere, you will have some free variables remaining. So you will always have independent variables and hence infinitely many solutions. So this, even if you didn't understand it, it's fine. If m is greater than n, you already know that, since you know about dimension and all that, you know that if you have more than the dimension number of vectors, then you'll run into problem anyway.
See, here we can just say that we have m equations and n variables, so one would be a free variable anyway. So we can.
Yes, since this is a homogeneous system, that is also one way of seeing it. You have more variables than the number of equations, right? Yeah.
Sir.
Excuse me, sir.
Sir.
Yeah.
So I have a doubt in one of the previous questions. Can you please go above? A bit above. More, sir. Yes, this example. Yes, yes.
Yeah.
Sir, in this example, we have two pivots, right? We said vector 1 and vector 2 will form bases. But now we are talking bases will be for linearly independent spanning set.
So this is something that will come later. But if you want, what I was saying earlier was that 1, 1, 2, 3, which is the first vector, and the second vector 1, 4, 5, 6 is a basis for span S. Span S is a subspace and its dimension is 2 and the basis is this. We'll get to that.
So
At that time, it
we
might be more
define
clear.
basis for linearly independent spanning set, right? This one is linearly dependent, this example.
So we don't define basis for a spanning set. We define basis for a vector space. And span S is a vector space. Irrespective of what S is, span S is a vector space. But S is not a basis because there is some dependence. That's why we have something smaller than S. So this is not a minimal spanning set. This is a spanning set for span S by definition, but this is not a minimal spanning set because there is some redundancy. And this method tells you that if you remove the third vector and just work with two vectors, that happens to be a basis for span S. The basis has to be linearly independent. It's not that, so I'm not saying that this thing is a basis. I'm not saying that set that we started out is a basis. We figured out that this two element set is a basis for the subspace which is span S. Is that okay?
Okay, sir.
Yes, sir.
All right. So that's about basis and how to construct basis. Here, this is something that I will not
Excuse me.
explain in detail. Yeah.
The earlier ones, the first one, just previous one.
This one?
Here, there are only two variables here, no, sir? X
There are
and
three
Y.
variables, x, y, and z, right? So if you were to solve a system of equations, there would be three variables. Otherwise, this matrix multiplication would not make sense. The number of columns is the number of variables, and the number of rows is the number of equations. So you have three columns, meaning three variables. So this is what? 2 cross 3. This has to be multiplied with the 3 cross 3.
But the vectors we have you have given is 1, 1, 1 minus 1, and a, b, no, sir? There are
Yes.
three vectors.
There are three vectors, yes.
With each one having two variables, right, sir?
Each one having two entries, but if you want to determine the linear dependence or independence of this, you have to do ax equal to 0 with these vectors as columns of A. So how many such vectors are there? There are three vectors that we are trying for. So there are three variables. So this would be A times x, y, z is equal to 0. This would be something of this sort. And this system has three variables, out of which one is independent. This one precisely. So what did we say over here? We said construct the matrix with VIS columns, call it A, and solve for AX equal to 0. What is AX equal to 0? It's a system of homogeneous system of linear equations with, in this case, m equations and n variables. This A is m cross n. If I have n vectors in Rm, this would be m cross n, which means that there are n variables. And in this case, what is that n? N is 3. We have three vectors, so we have three variables, x, y, z. That okay? So this constructing basis part is something I'll just mention, because finding the basis, at least from an examination point of view, only requires doing it when a spanning set is given. You can take a look at how this is done by revisiting the lecture videos. So you started with a null set, keep adding vectors linearly independent, such that at every stage you have a linearly independent set until you get a spanning set. That is one way, and deleting vectors. So this deleting vectors is something that we will, a more sophisticated way of deleting vectors is what we will see next. All right, okay, before we do that, over here, let me just mention every basis of a vector space has the same number of elements and that is called the dimension of the vector space. So coming back to this example, where was that? Yeah, this one, right? So we started out with a 3-element set S and looked at span of S. Span of S is a vector subspace. What we saw was there are only 2 linearly independent vectors in its basis. So this is not a basis. S itself is not a basis for span S. It's just a spanning set. It's not a minimal spanning set. But this is a basis because it spans by definition and it is linearly independent by construction. So it has 2 elements. So what is the dimension of span S?
5.
Sir, 2, sir. 2 is the dimension.
2.
Yeah, the size of the basis is the span. So the basis has only 2 elements. So in this case, the dimension of span S is 2. All right, so that is basis and dimension. Now, how do we getting basis when spanning set is given? So the first one is row method. Suppose W is equal to span of S. What we do is construct. So this is called the row method because we do this. Construct the matrix with vectors in S as rows. Get REF. The pivot rows form a basis. So this is the algorithm. Let's see with an example. Let's take some 1101, 2034. And for simplicity, I'll just take the sum of these two things, which is 3, 1, 3, 5. Now, is this a linearly independent set or dependent set by construction?
Dependent.
It is dependent.
This is dependent, sir. Last one is
Yeah.
sum of both.
Yeah. So what is a basis for span S? So in this case, it is easy to see that the first 2 elements will form a basis. But I'll tell you how to do the row method, which works more generally when it may not be obvious if one is a linear combination or which one is a linear combination of which other thing.
The third is a linear combination of the first two. So
in this case, yes. In general, it might not be clear, is what I'm saying. So we'll perform the steps detailed above, which is construct a matrix with vectors in S as rows. So earlier we were doing columns. So this is the row method. In this, you have to do it as rows and then row reduce. Get the REF. How would I do that? This would be 2 times I have to remove -2, 3, 2. 3 times I have to remove.
R3 minus 3 times R1.
This also should be the same. Yeah. And then I can further do one more step where I get 1 minus 3 by 2 minus 1, 0. So how many pivots are there? There are 2 pivots. So the dimension of span is 2.
So
And the
dimension
basis,
and bases are also.
so basis is a set, dimension is a number, basis is the pivot rows. So it is 1101 and 01 minus 3 by 2 1. So this is a basis for span. So there could be many other bases. As we have already seen, we could just take the first two vectors and get a basis itself. But as per the algorithm, what you would do is you just take the first two rows or the rows containing the pivot elements. That would be a basis for your span.
Yes.
So as soon
Means
as you have,
non-zero rows.
yes, the non-zero rows, and dimension is 2. This is as per the row method. But as you see, the row method will give you vectors which are not in, they might give you vectors which are not in your original set. If you want to find a subset of the original set that you started out with, original set being S, if you want to find a subset of the original set, which is actually a basis, then we use
So we'll
column method.
compute column method.
So in this case, what do you do is construct the matrix with vectors in S as columns, get REF, vectors corresponding to, what is corresponding to, I'll explain, pivots are basis vector, form of basis. The same three vectors we'll consider as before, but this time we'll write them as columns. It was what? 1101, 2034, 3135. So for the column formulation, we need to do this. So this is C1, C2, C3. Just let this be there over here. If I want to row reduce this, what will I do? I'll do 1, 2, 3, subtract it, minus 2, minus 2, 0, 3, 3, and 0, 2, 2. And one step further. As expected, the number of pivots are the same. But what columns do they correspond to? Where are the pivots?
So first and second.
First and second are pivots. So the first and second vector from the set that you started out with, which is 1101 and 2034, this forms a basis.
But sir, in the row method, as long as
Just
I'm
one
not
moment,
yeah.
let me finish this. Then dimension is 2. Yeah, go ahead.
In the row method instead of column method, as long as I don't swap a row, this corresponding thing can still be applicable there.
Yes, yes. That will be fine, because you're taking linear combinations of those things. If you don't swap, then you'll be okay.
Yeah, okay.
And even if you swap, if you keep track of what swap you're doing, and yeah, we discussed this in the live session. Yeah, I'll refer you to that if you want to take a look at it further.
Okay.
Yeah.
Excuse me, sir.
Yeah.
Sir, in this row reduced form in column C2 is 2100, but in the basis we are writing 2034. So can we do
Yes.
the same thing in row method as well? Is there some rule?
Yeah, in the row method, there are cases where you're asking if I just look at the row number and then look at the corresponding vector, will that work? Is what you're asking,
Yes,
right?
sir. Yes, sir. Because in column
That
also we have done the same thing.
Yeah, that will not work because when you do row echelon form, when you're row reducing, you might have swapped, and then because of zeros, you might have swapped, and now the track you have lost track of it. So for now, just take it as a thing that it can happen that if you just consider instead of taking these two vectors, if you say that this is R1 and R2 and I'll take vector 1 and vector 2, in this case it works. There are cases where it will not work. So for the row method, you have to just write the rows as it is.
Okay, got it, sir. And just one small doubt. Can you please go above? Uh, in that previous example which I asked earlier for the
This one?
basis one.
Yeah.
Yes. Yes. Here we have y is equal to minus 2z and x is equal to z, right? So
No,
we
x
got
is equal to
the
minus y minus z.
no, when we substitute the value of y,
Ah,
because
right,
y is
right, right,
minus
right,
2z.
right.
Yes. So
Yeah, yeah,
x
you'll
is
get
z
z.
and y is minus 2z.
Yeah.
Huh. So if we take z common, it will become 1, minus 2, and 1.
Yes.
So can I say this as null space? This is
Yes.
out of context, the doubt is.
Yes. Yes. 1 minus 2, 1 is a basis for the null space.
Basis for null space. Okay, sir. Thank you.
Just 1 minus 2, 1 or any non-zero multiple of that will also work.
Sir, one question. So
Yeah.
currently the first two vectors are the basis, right? What if the third is supposed to be basis? How does this row of uh, form would look?
Row, yeah. So if you had, so okay, let me write that as an example. If the REF of doing all of those things is, let's say, 101, 001, this can happen, right? It could even happen this way. Then V1, V3 would be the basis. Does this clarify your doubt?
Yes, thank you.
Yeah, the REF can have, it need not have always C1, C2, C3 in order. No, it can skip variables. As long
So
as it
which
is,
method is sorry? Which method is more efficient, the row method or the column method?
that I don't know.
So what can we use, the row or the column?
Either of them will work. And computationally,
Okay.
for a human, I think it both are similar only. I
Okay.
thought when you asked computational difficulty, if you have to code it, that I thought was what you were asking. That I don't.
No, no, sir. No, no, no. If we use either of the two, the answer is still correct, right?
Yes.
Okay.
Yeah. And then we have what is called rank of a matrix. Next, we have rank and nullity. So first, we'll do rank. What is rank of a matrix? Is the dimension of the column space. Rank of a matrix, let me call it A. Dimension of column space of A. What does this mean? So when I write a matrix A, it has certain columns, right? So suppose this is an M cross N matrix. How many column vectors does it have?
In
5.
Well, in this case, I've
And
written 5 as the number of lines, but over here I've said the order is N, right? So N columns,
in vectors.
and
Oh, there's a dog
these
barking.
are there. These N column vectors are in which space?
Column space.
The column space.
No. So what is the number of entries in them? They are in Rm is what I want to say. Okay, they are vectors in Rm. Correct?
Yes.
Yeah.
Yes, m rows
So
and n columns.
yeah, this span of set of column vectors. So what is this set column vectors? What is the cardinality of the set? What is the number? What is the size of this set? It is n. It's an set of n elements, and I'm looking at the span of that. That could have basis n or less, right? So this span of the set of column vectors is called column space. It's pretty much just what is column space? The space of all column vectors. The space spanned by the column vectors is column space. And the dimension of the column space is what we call rank of the matrix. Some facts is similarly you can have row space, which is once again by definition the vector space spanned by the row vectors. Now for the row vectors, the situation is different. These vectors are in Rn and there are m many of them. Right, but the fact is that dimension of row space is the same as dimension of column space. So strictly speaking, we have to say row rank and column rank, but because of this fact, both of them are equal, and it is equal to what is called the rank of the matrix. Now, how to find rank? Any of the following methods can be used to find rank. So by definition, we have already said it is dimension of column space, and given some vectors, you know how to find the dimension of the space that they span. Similarly, you can do it for row space also. This is the same thing said in different ways. Number of pivots in REF, or which is the same as number of non-zero rows in REF. Which is the same as number of dependent variables for AX equal to 0. Either of them, like all of them are the same, and that is equal to the rank of the matrix. So there can be questions where you are given a matrix where one entry is unknown. It's like some alpha or whatever, and then find the value of that alpha for which rank is equal to a specified number. What would you do? You row reduce it. And while you row reduce it, you will see that the number of pivots is dependent on the alpha. So there will only be one value of alpha, or sometimes finitely many values of alpha, for which the number of pivots matches whatever is asked in the question. So such questions, probably it's there in PYQ also. You can check that, try to solve it. But finding rank is pretty much just what we have been doing over here. We have been calling it a different name. We have been calling it the dimension of the. Even over here, what did we do? We took a bunch of vectors, arranged it in the as rows, and then found the number of pivots. That is just saying what is the dimension of the row space. In the column method, we are doing the dimension of the column space. So all of those are same, and it is called the rank of the matrix. And after rank, we have what is nullity of a matrix. Nullity of a matrix is more, in substance, natural. What is nullity? It is the set of all vector null space. So dimension of null space is called nullity. What is null space of a matrix?
Solution space for Ax equal to 0.
Yeah.
Solution space.
Yeah. X tilde in, let me call this m cross n. So this will be in Rn such that Ax tilde is 0. Now this is a subspace is something that we had seen as one of the examples of a vector space and vector subspace, or you can verify also. Now how to find the dimension of this? So once again, REF comes to the rescue. Get REF number of independent variables is equal to nullity. Nullity meaning dimension of null space. How do you get a basis for the null space? Is just by solving this system of linear equations. So let me give you an example. Solving a homogeneous system of equations is something that we have already seen in week 1 and week 2. But let us take some matrix, something like a 3 cross 4. I'll just write random stuff. Something like this. Find the nullity and maybe I would want something like this. I want some nullity. Okay, find nullity and a basis for the null space. So what is the REF of this? This is 0, 2, 2, 0, 3 times, go 3 times. Just do the calculations with me and let me know if there's any error. Two times this, something like this. Oh, for nullity, I should have taken 3 cross 4. All right. That's fine. So in this case, what are the pivots?
3.
There are 3 pivots. And how many variables are there?
6.
3 variables.
There are 3 variables. And all of the variables are?
Dependent. Independent.
They are dependent. So pivots are dependent variables.
Yes.
So nullity is equal
0.
to nullity is equal to 0. In this case, well, a basis would be just the empty set. Let me just flip this around and I'll say that I have a
Basis would be an empty set.
matrix.
So, but there is bases are 3.
Just one moment. Something like this. Suppose this is the REF of the matrix. So yeah, nullity is 0, meaning the null space is 0. And a basis for the trivial subspace is the empty set. So what is basis? What is nullity? Nullity is dimension of the null space, and dimension of the null space has to be 0, which means the number of elements in the basis has to be 0. What is a set with
So
0
this is
elements?
the basis of the null space.
This is basis of the null space, yeah.
So, but nullity and basis are the same?
Nullity is dimension of the basis of, nullity is dimension of null space,
Sir, in
which is,
lectures, there is something different. Like we can find nullity by the number of columns, like n minus basis.
n minus basis, n minus rank would be the thing.
That follows from the rank nullity theorem, right?
Yeah, that is just rank nullity theorem. So for now, you can just take that it as independent variables. In this case, there are no independent variables, so nullity is 0.
Here A is in R3, no, sir?
What is in R3?
A.
A is 4 cross 3. So what do you mean by A is in R3?
Means order is 3, no, sir? Rn R3.
The rows are in R3.
Ah, yes, sir.
The rows are in R3, but the null space is a subspace of R3. So is that what you're asking?
Yes, sir. Is it R3
Yeah.
or R4? I was, because you were doing like a column, writing the vectors in column as well as in rows. No? So I just wanted to confirm.
Yeah. So if you have a m cross n matrix, the solutions to Ax equal to 0, meaning that x has to come from Rn, right? So in this case, R3. You want to find x, y, z such that this is equal to this. So you are looking for this. So you are looking for solutions in R3.
Okay, sir.
Right. So okay. In this case, null space, if you want to write explicitly and precisely, it is this. 0 meaning 0, 0, 0 as a column vector, but we just write it as a row vector for convenience.
Can you tell how
Anyway,
nullity is 0 again? Because there are dependent variables, right? The pivots are the dependent variables.
yes, but
And
nullity is number of independent variables.
okay, and what are the independent variables here?
Here there are no independent variables because there are 3 variables, all of which are dependent.
Oh, that way. Oh, okay. And how is the basis empty? Is it because
Nullity is 0, meaning dimension of the null space is 0. And what is dimension? It is number of elements in the basis. Number of elements in the basis is 0, meaning it is the empty set. Or you can
okay? So
take it as a
nullity is 0.
convention that basis of the trivial subspace containing only one element is the empty set.
Okay, so if nullity is 0, base is also empty.
Basis is an empty set, yeah. Is the empty set.
Okay.
Yeah.
Yeah. Okay.
Sir,
Thank
in
you.
all such cases, nullity will be 0, no, sir. I mean, if m is not equal to n, then either we'll get a trivial solution or we'll get all linearly independent, all will be
No,
linearly dependent.
what if this was 0? This could also have happened, right?
Then it will be, I mean,
Then nullity will be 1. Would have been
how
1.
is 1?
So in this, if in place of this you had 0 over here, this entry, I've changed it to 0
Oh.
from 1.
So then we'll have 2 dependent variables and one independent variable and 2 dependent variables.
Yes. So nullity would be 1 because
Nullity.
it is the number of independent variables. Probably we have done such examples over here. Just one moment. Let me just go back to one of the examples. So take, for example, this one. If I look at this matrix, we started out with this matrix. Right? What is the nullity of this matrix? While row reducing it, I found that there were 2 pivot elements, which means that there were 2 dependent variables. So there's one independent variable, and nullity is 1.
Okay.
And yeah, suppose my REF is like this, just to demonstrate how to construct a basis. Suppose I have a matrix. After doing REF, I landed this thing. How many total variables are there and how many of them are independent?
Four variables and two
Four
dependent.
variables in total.
Independent is
1.
One.
and dependent is 3.
3.
So what is the rank of this matrix?
3, sir, and nullity is 1.
So this is rank nullity theorem. This leads to rank nullity theorem. We have defined nullity as number of independent variables, and we know that rank is number of dependent variables. So what is total number of independent variables and dependent variables? What is their sum? It is the total number of variables, which is the column number of columns. In this case, it is 4. In general, you have, let me write this over here, rank A plus nullity A is equal to number of columns. And both rank and nullity, the way to compute it is to get the REF and look at whichever you're interested in, dependent or independent variables. Now, how to construct a basis for the null space? Put or substitute. So what does it mean to say something is dependent and something is independent? Dependent can be expressed as a linear combination of independents. So in this case, you have x4 is equal to 0. You have x2 minus x3 plus 2x4 is equal to 0. And x1 plus x2, I've written it in the reverse order, but it's all right. This is equal to 0. So x3 is the independent variable. So I write everything else in terms of x3. x4 I can remove because x4 is 0 itself. So x2 is equal to x3 and x1 is equal to, now x3 is x2 or x2 is x3 and oh wait, here this will be x4, right? Yeah, and that is 0. So we'll have minus 3x3. So what would a typical element of the null space look like? It would look like minus 3x3 minus x3 x3 0. If you really want to be pedantic, you can call it 0x3. You can write it in terms of that. If you have more independent variables, you will have linear combinations of, suppose x3 and x5 was that were the independent variables, then you would have ax3 plus bx5 in every entry. And anyway, you can split them, and this can be written as x3 times minus 3, 1, 1, 0. So the single element set minus 3, 1, 1, 0 is a basis for the null space. In general, what you need to do is suppose you have suppose you have x3 and x5 as independent variables. You put x3 is equal to 1, x5 is equal to 0. You will get one vector. And then you do the other thing. x3 is equal to 0 and x5 is equal to 1. You'll get another vector. Those two vectors form a basis for the null space. I'll ask in the TA sessions for them to take up one example where there are at least two, when the nullity is at least 2. Here I don't have time to do that.
Sir, could you please explain why we have written that x4 is equal to 0 and then further we have got this? I did not
So
understand.
here, if you we are trying to solve for this equation, right? So when you expand this out, what would the last equation give you? X4 is equal to 0. That is the first thing that I've written over here.
Okay.
This corresponds to this, and this corresponds to this.
What is it?
Okay. So this is rank nullity, and quickly I'll just review linear transformations, and then let's stop. So linear transformations is the special class of functions which respect the linear structure. So in general, if I have a map between two spaces, this, and I have an addition and multiplication in each of them, these are vector spaces, then this is said to be a linear transformation. If addition is respected, meaning if you add and take the image, it's the same as taking the image and adding them. Where do these pluses, so this plus is in V, this plus is in W, all of these things you need to carefully see. This dot is in V and this dot is actually in W. No, this dot is in W and this dot is in V. So all of that is fine. This has to happen for all vectors. So scalar multiplication as well as addition, it does not matter in which order you do. You either take the image of the vectors and then do the addition or scalar multiplication on the target space, or you do it initially and then take the image of them. Both of them lead to the same thing. So that is a linear transformation. And in general, for functions, we know what is injective and surjective, right? Injective or one-to-one. What does this mean? This would mean that two different elements should not go to the same element. This should not happen. Or if t of x is equal to t of y, that should necessarily imply that x is equal to y. You cannot have non-equal xy such that tx is equal to ty. That should not happen. But in the case of linear transformations, this is only for linear transformations, that tx is equal to 0 implies x is equal to 0. T is injective if the following condition holds. In the general case, you have to ensure that there is no element in the codomain which is the target of two different elements in the domain. But in this case, what you have to do is just verify that the pre-image or the elements that are mapped to 0 is just 0. Only 0 is mapped to 0, and you don't need to care about anything else. So this is specifically for linear transformations. And surjective is something that is very well known or onto. For all W in W, which is the codomain, there exists a V in V such that T of V is W, which means that every element of the codomain has a pre-image. And injective means that it has at most one pre-image. So in other words, when you have injective and surjective, which is called bijective, and in the case of linear transformations, it's called a linear isomorphism. Every element has a unique pre-image. Every element has a pre-image and exactly one.
So could you please explain injective part in terms of vector space once again, please?
Which part do you want me to explain again?
The injective part.
Injective. Okay. So, okay, I'll explain with an example. Maybe then it will be clear. Injective and surgical. This is just like bijective linear transformation is called linear isomer. All right. So, suppose I take an example. This is from, let's say, R2 to R2. If I do just one moment. Something like 4x plus 2y and what would I need? 6x plus 3y. That's it. You have to verify that this is a linear transformation first. But let's try to see if this is injective or not. So if you want to verify whether some function is injective or not, what would you do? If you want to do the brute force method, you want to see if there exist x1, y1 and x2, y2 such that their images are equal. Such a thing should not happen unless x1, y1 is equal to x2, y2. This should not happen other than that case. But in this case, what would you end up getting? 4x1 plus 2y1, 6x1 plus 3y1 is equal to 4x2 plus 2y2, 6x2 plus 3y2. And if I compare the coordinates and rearrange and all that, I'll get 4 times x1 minus x2 plus 2 times y1 minus y2. This is equal to 0. And 6 times x1 minus x2. This is essentially the same equation. Three by 2, right? Yeah, 3 by 2. And if I solve this system of equations for x1 minus x2 and y1 minus y2, we will see that this has infinitely many solutions. For example, x1 minus x2 is equal to some t, and y1 minus y2 is equal to minus 2t. This will satisfy this system of equations. What I would need to say is, look at t of, let's say, 1 comma 0 and t of, let's say, 1 2 comma minus 2. Let's try this. Does this work? This doesn't work. Just one moment. Plus x2. y1 is equal to y2 minus 2t. Let's take t is equal to 1. If I have x2 is equal to 1, 0, and x1, x2, y2 is 1, 0, this would be 2 minus 2. And that's fine, I think. Okay. Just bear with me for a bit. I'll explain what I'm doing. What is T of 1, 0?
4,6. 4,6.
And what is T of 2, -2?
8 minus 4, which is 4, and 12 minus 6 is 6.
So you have two elements in the domain which are mapped to the same element and they are not equal. How I got it is a little bit confusing, but I'm just trying to tell you, in the case of linear equations, you can do it much in a far simpler way. But this is not injective. T is not injective. Is this clear? Because there are two unequal elements going to the same element in the codomain.
Yes, sir.
Right. But this was it. You did not need to do so much work because for linear transformations, we have the following property that Tx is equal to 0.
So could you please repeat this last part? How we got
So
two T of 2 minus 2 4 6?
this is just okay. Forget about this part. This whole thing you don't pay attention to. Just take the definition of this and observe that T of 1, 0 is 4, 6 and T of 2 minus 2 is also 4, 6. I just substitute 1, 0 in this and 2 minus 2 in this. I'll get 4, 4, 6 in both cases.
I think the
Where are
T
we
and minus
substituting 2 and minus 2?
For x
from the
and y.
second equation, right?
2
From the second
minus
equation, you can get it. Both equations you can get.
So 4 times 2 plus 2 times minus 2, which is 8 minus 4. That's the first
Got
coordinate.
it.
And 6 times 2 plus 3 times minus 2, which is 12 minus 6, which is 6. So the conclusion is that there are two elements in the domain which are mapped to the same element. So this is not injective. But life was actually much simpler because this is a linear transformation. You look at what are you look at the set of xy which is mapped to 0, 0. 0, 0 is always mapped to 0, 0. The 0 vector is always mapped to a 0 vector in the linear transformation. But are there others? Is what we are trying to see. So for that, you would solve the equation 4x plus 2y is equal to 0 and 6x plus 3y is equal to 0. Right? If I want to see what are the vectors which satisfy this equation, why? Because txy is just 4x plus 2y comma 6x plus 3y. And I compare the coordinates and I get the system of equations. The system of equations, one of them is a multiple of the other. So this is actually an infinite solution system. You can verify that by doing whichever method you like. Determinant is 0. So this has infinitely many solutions. So there are non-zero vectors which are mapped to 0 vector. That is why it is non-injective. So injective for a linear transformation, this is injective if and only if T of, I'll call this V now because it's in a general vector space. T of V is equal to 0 implies V is equal to 0. Or you try to look at all the vectors which are mapped to 0. If 0 is the only vector, then it is injective. If there are other vectors, then it is not injective. Is that fine?
Yes.
Yes, sir. Yes, sir.
Yeah. So that's injectivity, surjectivity, and isomorphism. There is one small topic which is how a basis determines a linear transformation. That I'll tell one of the TAs to take it up. Is that fine? In tomorrow's session.
Sir, could you please state one example of onto as well?
Could you repeat that? I couldn't hear you clearly.
Uh, could you please take just one example of onto for onto as well? Surjective function.
A surjective function. We don't know rank nullity here, right? So Determining surjectivity at this point is not very direct. You will have to solve a system of linear equations. So in this case, is this map surjective? Let's try to see that itself. That is where maybe we'll end. Now, injectivity, we established that it is not injective. Is it surjective? To see if it is surjective, what is an alternative way of formulating that question? Does every x0, y0 in R2 codomain have a pre-image? Pre-image meaning a vector which maps to this vector, which is mapped to this vector. So, or does there exist xy in R2 in a domain such that p of xy is equal to x0, y0? This has to happen for all x0, y0. If you try to solve this again, you will get 4x plus 6y is equal to x0 and 2x plus 3y is equal to y0. No, this was wrong. This was 2, this was 6. Just I'm substituting what the value for t is and comparing the coordinates. Now, will this system have a solution always, irrespective of what values you have for x0 and y0?
No, you cannot have, because of it has infinitely many solutions, right? So
Infinitely many solutions in a homogeneous case, but this could be non-homogeneous also. X0 and y0 could be anything.
yes. But when you take in the first equation, it's x plus 2x plus y equal to x naught by 2, and 2x plus y is also y naught by 2.
Y naught by 3.
Oh, 1 naught by 1 naught by 3, yes.
Yeah.
So
yeah, you're there. You're almost there. Just complete that argument.
yes. So, but from the first equation, we have this x plus 2y equal to x naught by 2. If we substitute that in the second equation, we'll have 3x naught equal to y naught.
Now let's write that itself. Now 2x plus y is equal to two different things. Now if those two things don't agree, then you will not have a solution, correct?
Yes.
If x naught by 2 is not equal to y naught by 3, then it will not be there. So take, for example, 2 comma 6. This will not have a pre-image. Maybe check that as an exercise. Check that does not have a pre-image.
Sir, like, since in this case the mapping is between R2 to R2, can we conclude when it is not injective, it is not surjective, right?
Yes, that you can conclude, but rank nullity for transformations is not a part of the syllabus, so I don't want to use that. But yeah, you guys have already done week 6 now. Yeah, if you know that, then it is easy to conclude, because here kernel being non-trivial means kernel is at least dimension 1. This is just for people who understand what kernel and image is. And if kernel has dimension 1, then image can have dimension at max 1. So it cannot be surjective. That is one more. That's why I paused when this question came up. I did not know whether or not to use this. But that is also one way. But even just by first principles, you can set up a system of equations and analyze the solution space and conclude that this is not surjective. Yeah, and I think this is a good place to stop. I'll tell the TAs to cover that using image of basis to derive the equation of a linear transformation. Or maybe I'll drop by on Saturday towards the end of the session to cover that. Do you think you need a longer session maybe on Saturday, maybe it's from 7:30 instead of 8 for problem solving session?
Yes, sir.
Yes, sir.
All right. I'll see if there is no clash with any other course. If that is the case, maybe we'll have it from 7:30.
So we have a clash with the stats.
Stats is also on Saturday, is it? There's a
Yeah,
session on
yeah,
Saturday.
yeah.
Oh, then I cannot do that. Going past 10, I cannot expect a TA to do that. I'll see.
Sir, why can't we from 8 to Saturday 10, 8 to 10:30?
Yeah, the thing is, TAs will also have to